Welcome to Real Physics. Today I have a guest, Martín López Corredoira from the, if I pronounce it correctly, Instituto de Astrofísicas de Canarias in Spain, in Tenerife. And we know each other for, I guess it's 12 years. We met personally. You kindly invited me back then to give a talk about the topic of my first book. And well, since then, I admit I have been a little bit jealous about your working place because it's a place where Germans used to go for a holiday and you work here. And so you are in the Canarias. Yeah, well, what's to say about Martín López Corredoira? He's a person with a very broad erudition. I just Googled you again, and you have got prizes in literature. What? And speak a couple of languages. I think we could even communicate in German, but the audience probably wouldn't enjoy that. So you have I don't know what degree, but you're also a philosopher. I think that's very remarkable in current times. And of course, you're here because you are a physicist and cosmologist. And even within that field, you're remarkably, broad in your interests. You have your very specific work as a researcher and doing, if I'm not mistaken, we can expand on that later, doing research on the spiral arm of the Milky Way and also on galaxies in general. You have been working on galaxy dynamics and you have an impressive number of, I think, 170 publications, 140 of them on the archive, so readers can easily look up what you're doing. But that's not it's not everything. You are also a critic of contemporary cosmology, if I may phrase it that way, or at least I would say you take a critical perspective, you just put in very interesting things. I remember a paper back then entitled The Sociology of Cosmology that attracted my attention to you. And you have published a couple of books in your specialized field about cosmology and also galaxies, and also about general physics. I enjoyed very much Against the Tide and The Twilight of Scientific Age, a book about the general status of science today. And you have even published in another field. I come back later. It's a little bit special, but I think we should mention that. And yeah, and that, among others, reveals that, I guess, what is the most important property of a scientist, you have courage. And that's rare in today's scientific environment. And therefore, I'm happy that you're here. Welcome to Real Physics, Martin.
Thank you very much for the invitation.
Should we go right into your, specialized work? I know you have been recently working, you have been in China, you have recently been working on topics like the variation of the fine structure constant in quasars, or about the oldest galaxies of redshift 8. What's the, if I may start, what's the most interesting, significant work what you find right now in the realm of your specialized work as a cosmologist and astrophysicist?
Well, at present, I have been working in the last couple of years about exactly the age of the galaxies at high redshift. Because we have the new data of the James Webb Space Telescope. This provides new information, so it's a new source of analysis, and I'm trying to do some analysis away from the mainstream line. The mainstream line, usually they assume the standard cosmology, the lambda CDM is the correct picture, and they try to adapt the observations to this picture. And when something does not work, they add a new element, or they try to fit the data in some way, always with the ansatz that the cosmology is correct. In my case, I try to say, well, here we see some galaxies that look problematic. They look maybe older than they should be expected at high redshift, even quite small, much smaller than it is expected. It's true that we can introduce new elements in the evolution of galaxies, in the galaxy formation, just to save the standard scenario. But it's also possible to understand these galaxies with alternative scenarios too. We should not be constrained. So this is part of my work, trying to understand the observations, not only with the standard picture, but with different scenarios. Particularly about the age of the galaxies, well, it's still too early to take any conclusion, but we are finding that there are galaxies which are too massive. They are galaxies almost like the Milky Way in size, or not in size, in mass at least. When the universe was very young, was 600, 700 megayears. So it's a little bit puzzling. It's a little bit difficult to understand how these galaxies were formed in such a short time. No? And moreover, we are trying to get some numbers, some approximations, because when we go to high redshift and we use some stellar models, we have to do approximations. We cannot be so accurate. This is not particle physics in which you can get numbers with high precision. No.
Okay.
Well, possibly particle physics is not the best example. You know more than me than that, but at least people try to get a high accuracy in particle physics, in astrophysics, and especially at high redshift. Things are more difficult. There are many approximations, the models of stellar formation, the IMF, the whatever. So we work with approximations. And within these approximations, I'm finding that, well, they look quite old, these galaxies, relatively old, maybe 1 gigayear or between 1 and 2 gigayears, plus minus some error bar that allows you maybe to be compatible, but not with a high confidence. I mean, maybe it's within 2, 3, 4 sigma, maybe it is compatible, but there is some tension. There is some tension with the standard model. And this is my work nowadays that I think is important. In the future, I will also touch the topic of the angular size, something that I was working in the past, but with the new data of the James Webb, I think there's a new source. It is well known, the problem, since many years ago, since almost 20, even more than 20 years, it is well known that the galaxies are much smaller at high redshift than in the local universe. The question is the explanation, whether there is a true evolution of the size of the galaxies for some mysterious reason that we don't understand still nowadays, or is it because we are applying the cosmological formula to convert angular distance into linear distance with a wrong cosmology? This is the question. And
what I would suspect.
yeah. Well, you have some work also about that, so you know about the topic. The problem, the thing is that we are going to very high redshift. We are reaching redshift 10 or around that. That is much higher than in the past. So the tension is much more evident.
Yeah. Very interesting. Just let me drop in for a more technical question. So you think that the data of the James Webb Telescope is really unique? That's just really something very sensational new from data quality from the redshift to 10, because they have evidently different instruments. And is it easy to access? Sometimes I had the impression, since I have been working sometimes with data, that it's a little bit more difficult technically to access the data, to do the data processing. I mean, earlier you could just, go to a site, download a file, and put it into Mathematica, and then was it. There are actually two questions: the technical access and the uniqueness of the data.
Well, I think James Webb is perhaps the best instrument that we have, but it's a continuation of what we have in the past. There were many other telescopes in the past. Also, the Space Telescope. We have the Hubble Space Telescope, was a fantastic telescope, providing a lot of fantastic data. Now we have gone one step beyond, and we have increased the distance at which we can see the galaxies. But the concept is the same. Simply, we are going 1 or 2 magnitudes deeper, but we are not observing something radically new. It's the same question.
No, the redshift a little bit more, because
a little bit more. Maybe with the Hubble, you could reach galaxies at redshift 8 or 10. Now we have the record, I think, redshift 14. This is something new. confirmed spectroscopically. I mean, then with a photometric redshift, even you can go to higher redshift. Yes, it's a question of better quality, but better quality, better numbers, more sensitivity. But we are observing the same kinds of objects, and we are doing the same astrophysics that we have been doing the last tens of years. We are not discovering a new universe. The only thing that is we are pushing more and more to the early times of the universe. About how easy it is to get the data, well, it's not so direct. Of course, you need to spend some time just to reducing the data or to get in the available tables that are already published. They are not, once the data are provided for the scientists that are responsible of a project, they are not immediately released to the community. You have to wait maybe 1 or 2 years. But after that, all the data should become publicly available. Anybody should be able to get this data with some delay with respect to the first release.
Well, I don't like it too much, but it's okay. Let's for well, undecided, but anyway, we can wait a little bit. So, is it? I mean, I like very much the unbiased approach. So, and of course, there are some technicalities to be done, like correcting for colors and filters, and maybe seeing or something that you won't. I mean, sometimes you don't want to mess with that because you're not introducing any preconception at this level. So how easy is it to get it, yeah, to data you can work with? So I once had SDSS, Slow and Digital Sky Survey. That was very easy, so to speak, to work with. Is it, yeah, with respect to that hard or I'm asking also because I mean being open means also being open to a broader community of scientists maybe, and if you put the entering bar very high on a technical level, so you're preventing non-specialists from entering the field, and this could be another hurdle for science as a matter of principle. So how is that?
In principle, they are the data are like in any other survey, like a Sloan, for instance. The images are in fits, so it's the same technique. The spectra can also be plotted in the same way. So there is nothing special. The only thing that there are, of course, there is plenty of information. It's a big survey with a lot of data. You have to know where to get the data. Nowadays, there is no a place, a centralized place where you can get everything of James Webb. It is distributed in several places, so one can become a little bit lost. If you are not a specialist, you have to spend some time just trying to know where the information is, because the spectra are in one place, perhaps the photometry is in another place, some part of the service are in different places. It supposes that in the future, there are like some web pages like Simbat or NED, that everything will be centralized and all the data will be provided there in only one place. But this is not available yet, so we have to wait. And the way to manage this data is the standard one. So as I said, if you get the table with the data, it's already reduced. You don't have to do anything. You have to trust that everything was correctly done, the photometry, the spectroscopy, whatever. You have the numbers. So you have your numbers, you convert your table in the format you want, and you work with your own codes. If you want to get directly the spectra or the images, they have standard formats also. Much nicer because they have a very high resolution. It's incredible. I'm quite amazed just to see that we can take a spectra of galaxies that are at redshift 8 or 10 almost, and see some lines even where you can see some features, and you can see that, of course, this is the O3 lines. You can say at least emission lines can be very well observed, so that they are fantastic, the data.
Yeah, I think that, by the way, I think this is a big advantage of cosmology, astrophysics with respect to particle physics, because there you have absolutely no chance. It's too specialized and too pre-processed. And this is, astrophysics is a fairly open community in this respect where you can analyze the data. And you said that the interesting result you're interested in large distances, and yeah, you mentioned also you had investigated earlier the angular size of galaxies. That was also before the James Webb Telescope. And yeah, can you point out the significance of that observation maybe for the standard model, or what would be very surprising for standard cosmology? If you're saying that the distant galaxies are smaller than expected, right?
Yes, and this is something that we knew in the past, but previously the surveys could reach redshift 3, 4, 5, 6 at most, but now we have the galaxies at redshift 10. And the most amazing thing is that we get galaxies with almost the same mass than the nearby ones, and with the size 10 times smaller on average.
Mhm.
10 times smaller on size is 1,000 more dense in the volume density, the mass density. So you can imagine that the stars are so close that it's impossible that they can keep attached. No? So we cannot explain how a galaxy can be so compact. We are talking about galaxies with almost the mass of the Milky Way concentrated in a size of 100 parsec or something like that. So the density is huge, the density of mass and the
And the parsecs are really, it's a geometric distance, say the hundreds of.
exactly. Well, what we obtain directly is the angular distance. This is the
Yeah, I
observable
mean,
amount.
once you establish distance, you have also
Once you establish the cosmology, because you need a cosmological model, you can convert angular distance into linear distance.
yeah.
We see that these galaxies are very small, are 0.1, zero point 0.2 arc seconds.
Mhm.
And you make the conversion with the standard formula for calculating the angular distance and so on, and
Mhm.
you get the linear distance. This is
Mhm.
straightforward. It's not, but the question is that
But do you see a clear contradiction here to the well standard model?
I
Or
see a clear problem. I think we have to investigate more. People who are attached to the standard model claim that evolution can solve anything. No, you
yeah,
said
I
they say
remember.
no. They say no. The galaxies have an evolution in size because they claim well there is some many mergers. You have small galaxies. There is a merger. You increase the angular momentum of the galaxy, and with this increase of the angular momentum, you increase the size. Okay, the concept might be fine. But the question is when you do the numbers, you try to do the numbers, how many mergers you need, and how many, it's very difficult to get such an increase
Yeah,
of size.
I mean, it's kind of difficult. I mean, mergers. I mean, yeah, of course, these things happen, but mathematically, we speak of zeros that
Mm,
things happening very rarely and not
mm,
regularly increase the size of the galaxies. And then something like the virial theorem, it's not subject to evolutions. It's just a law of physics. So,
mm.
I mean, I remember one of your papers, you said that the evolution has become a wild card inserted to explain everything. I mean, of course, if you're honest, it's a free parameter. If you want, evolution can do this and that. Uh,
Exactly.
that's kind of
It's like that because every time you go to high redshift, you have two factors: the cosmology and the evolution.
mhm,
Well, at least two. You have also the extinction. You can play with the amount of dust and many other things, but at least these two factors. And there is a degeneracy between the two factors generally. So you can keep constant the cosmology and play with the evolution, or do the opposite. Say that evolution is something more reasonable. Of course, we can understand that there may be some
mhm,
a light evolution in size or a
mhm.
light evolution in the stellar population, not but and then but then you have a problem with the cosmology. You have to change the cosmology.
Mhm, mhm. Yeah, I
Oh,
mean, I'm very interested in cosmology, but I don't want to go into alternative cosmologies yet because, I mean, maybe we disagree then too much. But yeah, let's just cover your I guess that's not the only thing which you did with your specialized expertise on was you want us to tell us something about the Milky Way, or you're more focused right now on distant galaxies, but I mean, you have to understand galaxies also before going into the universe out there, right? So Is there anything you must know about galaxies when you're observing these very distant objects? Because you certainly would analyze the bars out there at redshift 10 or something, right?
Now, there is people trying to do that and making the rotation curves at high redshift and so on. No, as you said at the beginning, I'm specialized in both fields, in the observational cosmology and Milky Way. Galaxies in general, but particularly about the Milky Way, not only the spiral arms, but about the center of the galaxy, the bulge, the long bar, and also the disk. We live in a spiral galaxy with which is a disk. Has
as a warp, that's something.
Exactly, it's a disk which is not totally flat, it's slightly warped, and there is some flare. That means the thickness of the disk is not constant, it changes. There are some elements that connect the dynamics of the galaxy with what we see, with the morphology, and we have to understand what is happening in the galaxy, which are the forces, whether there is dark matter or not dark matter, or whether, all these things, which was the evolution to form the galaxy. Well, this is connected with what we observe. And I think my opinion is that we know many things about the Milky Way. It's not so mysterious object. We know many things. It's true that with the last surveys, especially with Gaia, the mission Gaia, which we have obtained much better data, especially for the proper motions, for the astrometry, the precision, especially the precision. We can calculate the distance of many stars, and we can do much more accurate work with the galaxy. But fundamentally, if you are not a specialist, if you observe how is the field from outside, our picture of the Milky Way is more or less the same one than 50 years ago. So the picture is that we live in a normal spiral galaxy with a bar in the center. And this is more or less the time of the time in which it was formed is almost the age of the universe, so 13 billion years approximately. We know which is the part that were formed first, the halo, for instance, the globular cluster, and the central part of the galaxy. The disk was formed a little bit later. This was already known since many years ago. Now we are just confirming some things, just making more accurate measurements, extending the length or the distance at which we can observe.
Does the James Webb Telescope see red dwarfs to an unprecedented size? Smaller?
Of course, the James Webb can see many things, but it's not worth to dedicate such a big telescope for the Milky Way. For the Milky Way, it's more important, rather than observing a very small field with a lot of depth, it's better to have a large field, so to observe the whole sky and to have a big collection of stars, a complete survey. And in this case, as I said, Gaia is one case. The SLOAM, for instance, has provided not the whole sky, but at least 25–30% of the sky. There is in China, they have LAMOS for making spectroscopy of some part of the sky. There are many surveys specialized to investigate the Milky Way, and possibly they are not very, very deep, but they dedicate a lot of time to sample all the sky. So you can make a statistic with that.
Very good, yeah. One topic I have also always very interested in, but maybe I overestimated, the issue of tangential and radial velocities. I mean, of course, we have a preconception because we believe in the law of gravitation. So as a matter of principle, the motion should be circular. You have the virial theorem and all that stuff. But I mean, if you go strictly to observation, could it be that there is an anomaly regarding radial motion, which is not very visible at first sight, that may even interfere with dark matter explanations? What's the status of? How exactly do we know the direction of the outer parts of galaxies, the direction of the velocity, and limits on the radial part?
The answer is that yes, we know nowadays with the last data that there are some radial motions. So especially in the outer part of the disk, there are small radial motions. I mean, a few 10 or 20 kilometers per second, which is much smaller.
Outside or inside?
Outside.
Outside.
No, the motions can be outside and inside. The motions can be in any direction. But I mean, the absolute value of this radial motion is more important outside, in the outer part. In the inner part, the orbits are
No, I mean
quite circular.
the direction of the is it outwards or inwards? If there is
Both. Depends on the direction you look for.
okay. No systematic, no systematic.
It's not systematic. There is not an expansion or contraction of the galaxy as a whole. Depends. In some regions of the sky, it is expanding. Other regions are contracting, and there are small motions. You have said that if we assume that the galaxy is virialized, the orbits should be quite close to circularity, but the problem is that in the very outer part of the galaxy there is no equilibrium. The galaxy has not time to reach the equilibrium yet, so it's not totally virialized. This is what we have compared with some models of formation, and this is what we obtained. The explanation why we have some small component of radial motion is the non-equilibrium. In any case, this does not change the previous problem of the rotation curve and the connection with the dark matter. These radial motions are still very small to modify the necessity to introduce something else. You know perfectly that the rotation curves was one of the elements to introduce the dark matter, the non-baryon dark matter.
The most solid evidences.
Well, it's one of them. There are many, the clusters of galaxies. There is cosmology, also the CMB. There are many things, but perhaps the most popular is the rotation curves. This necessity is still there. No, we cannot explain the rotation curves with the observed light of the star in most of the stars.
But it's in that very region of low acceleration where you said that the motion is not yet settled. There is still, it's not yet in equilibrium. We're talking about the regions of very small accelerations where we postulate dark matter, right?
Yes, exactly. Yes, and this affect, but since these motions are very small, we are talking about 10, 20 kilometers per second. When you make the calculations, the necessity of dark matter remains more or less, because the circular velocity, the tangential velocity is around 200, 250 kilometers per second, is much higher than the radial velocities. Nowadays, there is some discussion, if you examine the literature from my group also, me and some collaborators, but other people too, they are finding that the rotation curve in the outer part, in the very outer part of the galaxy, in the Milky Way, is not totally flat, as it will be expected.
Yeah, it's a kind of wiggle. But
But apart from fluctuation, is falling down, slightly falling down. It's not Keplerian. So Keplerian will mean that you have all the mass in the center of the galaxy and there is no dark matter, but it's not totally flat as will be expected by the standard models of dark matter, in which you have the halo, the Navarro, Frank and White models and this thing. So we are doing some advance in the sense that some data that have been not some years ago, and there is some discussion. Still, well, we need something. Still, we need, but the numbers that we are obtaining now mean that the amount of dark matter maybe is lower than we thought in the past. Still, we need some dark matter, but not as much. And there are many possibilities. I know some colleague from Italy that I was working with him. He has the idea that maybe the dark matter is not in the halo, but is in the disk of the galaxy. And
but wouldn't that contradict the globular cluster motion?
Well, it has some differences, especially for the vertical motion, but not for the rotation curves. It's something that is not an original idea. I think this idea came from Bosma in the 70s, in the 80s, and it was discussed. The thing is that it was several times rejected, but not totally rejected, and people have kept this idea reviving it from time to time, and there are still people working on that.
Yeah, I mean, it's a riddle. I mean, I guess I can claim it's solved. Just from an observational point of view, one question. I mean, how much of the evidence is actually obtained from our Milky Way? I mean, I guess you're referring your work dealing with that, or I mean, what I remembered is what because we are in a difficult position as observers in our own galaxies, that the best evidence or the cleanest stuff are the nearby galaxies where we have the flat rotation curves, right? Or what's the value of what's the quality of the evidence? Our Milky Way indicating dark matter, or the other nearby galaxies?
The Milky Way has one advantage, that we have the stars are much closer, we have much more information, but we have one disadvantage, that we are embedded in the disk of the Milky Way. So it's not the same observing the galaxy from outside, that you can take the picture, the global picture, and also you can measure the rotation curve, measuring the distance from the center of the galaxy directly, just observing the galaxy as a whole. From the Milky Way, you need more other assumptions. So sometimes it's more difficult. Even if we have more information, it's not so direct, the information. To obtain a rotation curve in the Milky Way is more difficult than obtaining a rotation curve in other galaxies. On the other hand, if you ask me again about which is the stronger evidence for particular for dark matter or modified gravities, you want to have an alternative or whatever. Well, dark matter, the rotation curves are one popular topic, but the key issue to understand the necessity of the dark matter, the non-baryonic dark matter, is the CMB, is the cosmic microwave background radiation and the anisotropies of the cosmic microwave background radiation. Because if you have no dark matter at all, imagine a universe like the standard universe, the Friedman, Lemaitre, Robertson, Walker universe, but you suppress, you say there is not any kinds of dark matter, not hot dark matter, no cold dark matter. Well, in this case, the anisotropies of the CMB will be much larger. And this was predicted.
Come back to that later. I will try to remember, write it down. Just one point before. I have perceived you very neutral. I really like that always. So you're not advocating the standard model, but I have not seen either that you're advocating MOND theories. And so I think. Do you have also observations which would contradict the alternative, the MOND theory here, or?
There are not only my observations, but there are. I have read several papers that they have some tensions and what is happened. Well, many aspects. One of the most famous cases, the Ballet clusters, for instance, the people that have observed the distribution of the dark matter and the distribution of the gravitational lensing is different. And well, there are several things that, I know that MOND people, they trust their models and they can give ad hoc any kind of explanation for their observation, like a standard model people is the same game. But there are some doubts that, of course, in my opinion, even more doubts than in the mainstream science. So.
I see. So as a philosophy of an observer, you are a little bit like the guy I once talked to and say, which model do you prefer? And he retorted, I'd like to destroy them all. So you're just critically evaluating the evidence for that stuff. Yeah. Very interesting. The stuff about let's say the galactic level, the galaxy dynamics. If you return again to the universe, to more cosmological issues, specifically dark energy. What's your take on that? Or you're not specialized in supernova data, or I don't know, or have you done?
Well, I have published a paper on that. Yes, I'm not a specialist in supernova in the reduction of data and analysis, but I have taken the same data that are publicly available for everybody, and I have tried to understand this data.
I found it. I just tried a glimpse to look at these supernova. I find it incredibly difficult to in a mess of different colors and filters and evolutions and light curves. So
it's a quite technical question. It's the calibration, the templates, because people is assuming there is a template of the supernova. You can extrapolate and assume this template is here the same that at high redshift. You need some technical operations that are not trivial. You need to be a specialist for that. But assuming the technical work is correct, let's assume that the magnitudes are correct and the light curves are correct. Well, it's true that, as you know, 25 years ago exactly, or 26, it was discovered that the supernova at high redshift are fainter than would be expected if there were no dark energy. So dark energy was introduced to try to understand this small dimming of the supernova. It's very small. We're talking about at a redshift 1, maybe it's 0.2 magnitudes or so, but it was the error bars were small enough to put some constraint. And the conclusion is that we need to introduce dark energy in order to explain why the supernova are slightly fainter in apparent magnitude. No?
Yeah.
Of course, there are alternative explanations. This is the question. Dark energy is a good one. Nobody said the opposite, but there are other ideas. I can make a long list of possible ideas. Well, one of them, my favorite ones.
I think it was kind of 47 theoretical proposals to account.
No, not so many, and none of them is mine.
I'm serious. I counted that because a lot. I mean, different names. But I mean, the principal objection, or I think people are not focusing enough, is this very strange thing that in first approximation, you don't observe a deceleration because that's what you expect from conventional physics, from be it Einsteinian or Newtonian gravity. You expect that that expansion of the universe, if it is one, to be decelerated. And now you're just observing that's not happening. And instead of saying, okay, we might be mistaken, there might be something fundamentally wrong, people are introducing that free parameter and say, oh, it's going to be accelerated the very same amount we expected the deceleration, which is not observed. So I think, yeah, that's known as the coincidence problem. And well, I'm far from claiming that I understood or I have a viable model or whatever, but I think that's the key point that we haven't been attentive enough to. Yeah, what would be your take on that? Do you think, I mean, there are people claiming that this is ruled out, this zero acceleration model, but I guess, yeah, at the very end, you have to be very, very careful to introduce a new parameter that's adaptable to data, right?
My impression is that supernova alone cannot provide a definitive argument in favor of dark energy. You need something else. And it's very difficult because at present we cannot have any kind of observation to obtain any clue of what is the nature of dark energy. We only observe the consequences in gravity or in cosmology. It's even more difficult than in dark matter. Dark matter, at least we have some speculative ideas. Maybe it's cold dark matter, maybe hot dark matter, maybe some kinds of axions or some strange particles or whatever. There are many ideas, but dark energy, we don't have any idea what is the nature of dark energy. It's some kind of negative pressure of the universe, but it's very.
I agree.
So there is not any theoretical background behind. And the effects, well, yes, it's compatible what we see in CMB, for instance, the cosmic microwave background, with the supernova and some few other observations, gravitational lensing especially. But there are other observations which are in tension with this thing. For instance, the statistics about the amount of clusters of galaxies, apparently some years ago, has some tension with this number of omega lambda 0.7. Second, well, there are many ways to play with the models. For instance, for CMB, it's true that the same dark matter and same dark energy that is introduced in supernova can be introduced for the CMB and is compatible, but you can modify other parameters and produce a different value of dark energy too. So there is some degeneracy of values, particularly about the Hubble constant and the dark energy. There is some degeneracy. If you fix one, maybe you can get the other, but you cannot get everything at the same time from zero. And the thing is again a technical question. The thing is that it's not so simple, and maybe we are trusting too much one possible direction. That is a nice idea. The idea that we have dark energy. Why not? We should contemplate, but we are betting too much effort in one direction, and we should think about other possibilities. And there are many other possibilities. Some of them more exotic, some of them even simpler. From what I could read in the last years about the supernova question, for me was very interesting. It was a group in South Korea specialized in supernova who was making a study of the local supernova. And they found that it's not totally true that the supernova are standard candles. They are not perfect standard candles. So they depend on the age of the supernova. They depend slightly on the metallicity. Depends on several conditions. This happy idea of supernova are exactly the same with the same luminosity everywhere in the universe is not. It's more or less correct, but if you go very accurately to some tenths of magnitude, maybe it's not correct.
I'm happy that you refer to such work because that's a pattern I observe generally in science. I mean, sometimes it is terribly difficult, technically challenging, but there is a certain bias in the scientist. It's much easier to see evidence for the grand idea, for the visionary new introduction of a concept, than, let's say, to dig into the dirtiness of light filters, or if you go to particle physics, you go into the detector and photomultiplier stuff and all that, dirty stuff of an experiment, the nasty stuff that can introduce systematic errors. It's much less rewarding for a scientist to dig into there. So I'm really glad that you mentioned such work. And yeah, maybe, I mean, if we have covered, we cannot cover everything. I refer the audience also to the comments. I list the papers of Martin here, but I think we cannot cover everything. Maybe it's a good point to switch here to sociology. You said before that the supernova data alone cannot provide good evidence for the concept of dark energy. But I would say here, well, careful, because I mean, in science, you have this effect that at a certain turning point, the public is convinced that something exists. Okay, let's say the public in the sense of scientists. So once you reach that culmination of the turning point, that spectacular evidence, the publication in Nature in 1998 or I think it was 1998. The rest of the scientific community is, I mean, maybe too eagerly looking in their data to also find that same established concept now. And this is clearly, I mean, where sociology and confirmation bias comes into play. Well, first part would be, I mean, don't you see that effect a little bit in regarding dark energy? And second, more generally, what prompted you to investigate, I mean, these issues like sociology, how scientific communities work? What prompted you to dedicate your research to also?
Totally in agreement with what you have said, not only about the dark energy, but about cosmology. You are totally right. Once some concept is sacred in some way, and we give a Nobel Prize, for instance, the Nobel Prize of 2011 to Rees, people not only
It's merit.
Not only the general public, the amateurs, but also professional. They don't dare to say something against this concept. They say that they are forever. Yeah? They say, okay, but Rees got the Nobel Prize, so this means that it's like somebody won the war. Something, there is no discussion anymore about this concept. It was consecrated forever, no? And this is wrong. Well, in any case, we should not. We should bear in mind that the science is a very slow process. It takes many generations just to filter the good and the bad ideas. And sometimes we are wrong. We are following, maybe in a period of time, we are during half a century or even longer, we can be following wrong ideas, and later future generations will realize how much is the effect of the social factor. I think it's strong, especially in the most speculative sciences. Science like cosmology, particle physics, also that you know much better than me, in which there are some elements of speculation, and there are many possible ideas, many hypotheses that have to compete with each other. Which is the winner? Who is the winner? The one that makes more publicity, the one that organizes the conference, the one that makes the reviews of. In some sense, it's like a capitalism in our society. Those that have the power and control the mass media, they will give you the truth about what is in physics or about the Ukraine or about
results like in a capitalist economy, and no matter if it's useful or not. So yeah.
And then there is some vicious circle in the question that the more powerful is a group of research, the more money they get. No, I mean it's not. It's not democratic in some sense that we are dividing the budget for all the researchers with interesting ideas. No, there are some dominant groups that are taking all the resources, the most important resources for observations, for making experiments in particle physics, for publications, organizing conference, having lots of students, postdocs. They have all the resources, and the rest of the people are alone, basically, and they have to surrender in some case and to say, okay, either we join with the big group or we are isolated, and even we can jeopardize our careers, especially for young people. Nowadays, it's not my case. Unfortunately, I do not need to apply for a new position now, but young people have a very strong competition.
That's why you can speak out, maybe.
Well, I was speaking also when I was young, but I think this thing has become much worse in the last 20 or 30 years, particularly in cosmology. In cosmology, maybe in the 90s or so, even you could discuss some crazy ideas, and it was possible. No? Nowadays, you are marginalized in the best of the cases, and particularly if you are a young person, a PhD, recent PhD, or a young postdoc. If you start to dedicate an important part of your time to do research in some alternative ideas, or to make criticism, or to say that all this work of the dark energy with supernovae is not good enough, and we have to. Well, the thing is that possibly you will get some paper published that nobody will read, but in the end, when you go to apply for a new postdoc or a new position, you will have a much more difficult probability to get accepted, no? Because people want the people that they work in the same ideas that they work, no? This is the problem of science. If you ask me which is the fundamental problems of science nowadays, is that the creativity is not rewarded. Instead of promoting that young people produce new ideas, to produce new revolutions in science, is exactly the opposite. We have become very conservative. We try to keep alive something that maybe it's quite good in some cases, but in other cases, like cosmology, has many problems. But there are a lot of economical interests. There is a lot of business behind that, and people attach to this because it's part of their business. Simply like that, it's like defending a trademark in the market.
Yeah. I think that's a really important point. Yeah. That you're not encouraged, and that's, I mean, yeah, but I mean, the principal reason is indeed psychological, sociological pressure. Solomon Asch's confirmation experiment. I mean, but there must be personally. What is the reason for you that you took up on that issue? Was there something that happened to you? I mean, was it your philosophical erudition? Was it, I mean, what brought you and not other scientists working in your field? I mean, yeah, also speaking out and publishing. I mean, there are many people talking all the way, and you get an impression what you hear from. But I mean, you had the courage to, yeah, to write about this. Why?
Well, I don't know the reasons of other people. I think there are many people also thinking about these questions. Either they're right or not is not the question, but they think
Yeah, but it's
about it.
important. It's
Yeah.
important.
For
Yeah.
me, it's not a personal thing. It's not something that my career was so difficult that in revenge I want to fight against the mainstream. It's not like that. I have
Yeah.
many facilities in my research center. I have some freedom, a relatively freedom to do my own research. So I have not a personal complaint for myself. I think it's more connected with my interest both in the humanistic aspects of science and the technical part of science. I'm in the middle of the two parts. I think as a scientist, but I also think as a philosopher, as a sociologist in some sense. And there is a tradition that we are losing, unfortunately, but there is a tradition that the science should be critical with themselves, should be even skeptical. Skepticism is better than becoming dogmatic in some sense. We are not producing new truths. Science is a method. It's not a revelation. It's not a religion. I don't
Yeah.
I don't understand the scientists, some of my colleagues that when they say, I believe this or I believe that, that doesn't matter what you believe or not. I do not believe anything. Which is the reality, the Big Bang or the MOND or I don't know. I'm just doing my work. It's a technical science. Is a very beautiful work, but it's a technical work just to finding the evidence. It's a game trying to find evidences to support some theory or not, to reject other theories. We are, I think, our profession is like a lawyer, a lawyer defending some person, yes, some crime or that is innocent or guilty or whatever. A lawyer should not have any belief. The lawyer should apply the law simply.
The judge, yeah. I mean, the one.
The judge, but the lawyer, even defending some. Should be able to defend anybody. I mean, should be quite neutral. Of course, once you have your customer, your person you are going to defend, you try to find the arguments to defend him or her. But should be able to do the opposite thing in any case, because should be not based on something dogmatic that is inside you. You have to apply your knowledge, your best knowledge. In the case of the lawyer is the law, and in the case of scientists is physics and mathematics and astronomy and observation. And I think this instrumental approach is in some cases better than the becoming dogmatic a priori, no? Because this thing of I'm going to confirm this theory. No, you are not going to confirm anything. You are going to make the observations, and there are some theories in the literature, and you can compare one thing with another, but we should not go in one direction before we have the data. First, you observe, and then you take the conclusions. But some people is not. Some people, they have the conclusions before the observations. They go to make the observations. If they work, they make a lot of ballyhoo. They say, "Oh, we have confirmed the model. This is the true reality forever, and all the opposite ideas are wrong." And if it doesn't work, they say, "Well, we have to make some corrections of the model, and we to introduce some ad hoc correction."
I see. That's the way it works. Yeah, I see.
This is how it works, and this bad practice of the science is originated in having these strong convictions that there is some reality that we can't touch with our hand. Possibly in many aspects in science, of course, we have many absolute truths. If we are going to discuss whether the moon has craters or not, or we are going to, or if there are sun spots on the sun, or these kinds of things that Galileo has discovered, I think they are already totally accepted. Or whether the Earth is flat or spherical, I think we should not be so open to all kinds of ideas.
Your brain drops out. Yeah,
exactly. There are things that are definitively there, and we will not change anything. They are forever. But if you go to the frontier of science, particularly cosmology is in the border of what we can know and we can speculate. It's half science, half philosophy, half speculation. or particle physics, or in biology also there are many things that are discussed. So if you go to the border in which the contents of the science are not clear yet, and we are still discussing, we should not attach to any idea. We should not say, I am a defender of this idea. No, you should just do your work as the best you can do, of course. It's impossible. I know it's impossible to have this neutrality. We are not machines. We are humans, and possibly a person that has been working in some within the frame of some theory finds normal to work within this frame and not in an alternative idea.
I see.
But it's quite normal. But in any case, we should not forget that science is just a method to approach to a possible reality. It's not
ideally.
Ideally. In some cases, we never get the total truth. But this idea that we can get definitive answers in some very complex questions, like to know the beginning of the universe, how all the universe was formed, all the history, I think is somewhat too ambitious. We are
too prone to fantasy, right.
Yeah, exactly. It's a delusion of grandeur, I would say, in some sense. No, we feel that in 1 century we have it was just Einstein finished the general relativity, and a few years later some models of the universe arise. Even without data, no, they have produced the first Friedman models. Einstein produces also a cosmological model, a static cosmological model that then he will reject. And many others. But these ideas should not be produced so soon. They need further evidence. This idea that we can produce just because we are so intelligent and we have a very elegant mathematics, let's try to invent a new model. This is not in my opinion, I am more an empiricist, I would say. Maybe it's my bias also, but it's not the correct way to do the science. In astronomy, inductive method is definitely the most appropriate, with few exceptions. If you talk me about Einstein, the general relativity is an exception. It's a very brilliant exception, but most science is not produced in this way. Most science is that you observe. After you observe, you made your model, but not before.
Well, this is an issue of the inductive and deductive method. Yes, yeah. You talked of kind of a psychology of scientists also. I want to come back a little bit to the sociology, because I think it's very relevant. And you were saying that you're not a troubleshooter because you like to be a troubleshooter, as I would say that for me too, but you're just neutral, in a neutral manner, trying to observe what is going on. But I mean, you have been a little bit provocative also. So I guess it was one of your papers where you're saying that what do have cosmology and the oldest business in the world, what do they have in common, or something like that, or the sociology? Have you been attacked for that, or because, well, also in your book, then you're depicting kind of a grim picture of it's a history of science, very profound, I would say. But it's, you said Twilight, but I found it almost a dark picture of science.
Well, sometimes I have discussions with people, they don't like my ideas. Also, I receive sometimes support of other people, so not everybody is against to be critical. The thing, and even there are people who thank me just to express the ideas that everybody can think, but they don't dare to express. So somebody has to do it in some sense. Possibly I'm provocative, yes, but this is a method also. I mean, just if you try to produce some reaction, this is a way to make people think in some sense. Otherwise, they are very comfortable with their houses and their permanent position, just making their routine science and just they think this is something that will be forever, no? And you have to say, look, that possibly all your science is just something temporary, and within 30 years we will have to throw to the dustbin all your papers because we have to start in a new place. And science is like this. And I know this kinds of criticism is uncomfortable for some scientists, but are necessary. In any case, I don't think it's just pure entertainment, just pure joking with the people. I try to say serious things behind that. When I wrote this article that you mentioned, it was what has the astrophysics and the world's oldest profession in common. It was the title, insinuating, not directly, but insinuating that many of the researchers give more importance to getting funding. So yes, money.
Being passionate about the thing they're doing.
That the thing they are doing. The truth is not the most important thing for many scientists, but just getting some big project. If they can get an ERC project or something like that. I know this happens everywhere. It's not astrophysics, in science, in culture in general, art, everywhere. No? But possibly we are exaggerating the role of the money nowadays. Money should be an instrument. We need, of course, we need to build telescopes. We need to spend money in many things, but we should focus on what is important.
Yeah, but we should not stop to be truth seekers. I mean, that's the difference. I don't mind people making money somewhere else in society. Should they? It's fine. But I mean, as a scientist, you're committed to be truthful in the first place, right?
Yes, exactly. This is the traditional value of science is just searching the truth, like the traditional value of art is searching for beauty. And well, there are some values, the traditional values, but this thing that everything has to become a market and a competition just to get the position without any value, just producing a lot of papers without any value, just because you can increase your curriculum and get the next position. This kind.
Yeah.
This is a machine. We are converting science in some kind of a machine without soul. It's just a industry. We are making industrial science, and we should not forget that the most important thing in science are the ideas. And this spiritual part of science, just thinking and being innovation, also creating new ideas, being intelligent, not being able to get a project with hundreds of millions of euros and getting a new instrument and convincing the politicians to go beyond. And this is not our competition. Our competition is to get the best representation of the reality. But of course, we live in the time in which we live. We live in the capitalism. I think I agree with you, Alexander, in many aspects, because I have read also some of your books, particularly the one about America.
You mean comparing the tradition of European?
Exactly. The traditional, the German culture, the German science produces in the beginning of 20th century. And
Wait, I don't think I focused so much on Germany. I really intended Europe. I mean, it was clear that at the beginning of the 20th century, Germany was ahead also with respect to other nations, but I mean, we had all these phases in France and England, everywhere in Europe.
Yes, France was also important, of course. Yes,
centuries.
But this is what I mean. The science has become something industrial. We are producing just like we produce any cars and computers, and we produce papers in the same way. And we need some more artistic, something more artistic, and something more less productive with more intensity, I will say, and this is something that people do not want to enter in this direction because they see it is not a good way for their careers. You say some young person, imagine you say, okay, you should dedicate to 4 or 5 years to finish your work. Don't publish anything before. The student or the postdoc will say, no, I cannot do that because if I don't publish anything in 5 years, I cannot get a renewal of my contract. Or I have to apply every 2 years. I have to get a new postdoc. I know many postdocs, for instance, that they have very short contracts, maybe 1 or 2 years. And half of the time of the contract, they are preparing for applying for the next contract. So it's crazy. So you spend 6 months working, and in the last 6 months, you start to send curriculums everywhere and to make interviews everywhere. You spend a lot of time just in this competition for positions. No.
Well, wait.
this is what is sick in our environment nowadays. This kind of economical dependent question and everything, and other factors too. We are also, I recognize we are too many in astrophysics, but in many other science. It's good that science is available to everybody, but possibly we should ask why we have so many scientists nowadays, because nowadays there are millions and millions of scientists
Job rather than a profession. Yeah, yeah.
doing fundamental research only, apart from the application. Applied science is another thing. Of course, if you are an engineer or software development, or it is another thing. But just doing fundamental science, so many people possibly is not the most efficient way for the profession, because it's produced that we are making like a big jail in which everybody is watching over each other. I am the referee of you, and you are the referee of me, and we have to be in so many committees. So we are just controlling to each other, and we are not efficient. It will be better just to leave the people work. Yes, you go to your office with your colleagues, not necessarily isolated. You do your work, and when you have something to say, come and you say. But it's not how science works nowadays.
Yeah, yeah. No, I mean, I just observed that, as you said, people are under constant pressure to produce papers you're not supposed to not published for 6 months. I mean, Kepler needed 10 years to think about Newton, 10 years to think about their most significant work. So we have really a totally different environment. And well, my idea was that there was a change in the midst of the past century. I mean, the watershed is a little bit the shift of the dominating power from Europe, from the European countries to the United States. And I guess this changed science considerably. Also, in this respect, as you mentioned, it has become a business. You're focused on output. You don't want any more explanations. You're just getting stuff done and produce experiments and results and free parameters to model that. But that's an entirely different approach. I'm not being anti-American in any way, but just as an observation, I recognize their achievements. I mean, many things in applied science wouldn't have been possible without that mindset. But I think we should see that watershed also in scientific culture, right? So, yeah.
But we are not prepared to do anything yet. We have possibly, if there is some next revolution in science, it will be coincident with a revolution in our society. Once we change how the society is organized, the economy and the politics, and how people produce culture, then we may think in some new ideas in science. Meanwhile, we are going to do the same things. We are producing again and again. When we are in a circle producing the same ideas, because we have converted the culture in a business. Simply, no, we don't want something definitively new. And in the case we find some evidences observationally, for instance, these James Webb galaxies. In this case, instead of using these galaxies to produce new ideas, is the opposite. They try to put obstacles, no, to say, okay, no, but you have not taken into account this effect, and we are going to invent a new effect to preserve the past, no, because deeply people that they say one thing and they do another thing. People will say, no, we want innovation. False. They don't want innovation. They want to preserve what they have. We are desperate to get new physics. Everybody is happy with the idea. Yes, it will be fantastic to discover a new force in physics or a new particle. This is what they say. But at the same time, every time somebody proposes a new idea, they are rejecting this idea.
So the condition for achieving that. Yeah,
exactly.
Yeah. I really like that you have, I mean, the one hand side, these very detailed expertise of looking into that data. On the other hand, this very detached view. If I remember correctly, your book about the twilight of scientific age, it was a description of history as if everything else except Darwin and Newton, so to speak, was, I mean, that was almost the only settled science settled science you considered and said that, yeah, well, everything else we're doing, we're trying, but yeah, not be sure. You're taking that very philosophical, detached perspective.
Well, not so much, of course. I was not
Maybe
saying
I
that
exaggerate.
not
What's your
Darwin
take
and
on
Newton are the only
it?
scientists.
Really, you went into history, yeah? If you,
What I mean with this message of the twilight of the scientific age is that the science has a golden age in the past. Everybody knows what is a golden age, an epoch in which you produce a lot of fantastic ideas, a lot of fantastic advancement. And now we are not reaching the death still, but we are decreasing this rhythm. This means we don't have so many fantastic discoveries as in the past. We have many papers, we have many conferences, there is a lot of scientists, a lot of money, but this does not mean that we have many revolutions in science. If you have a look at the results of physics in the last 50 years, and you compare with the first 50 years in the 20th century, of course, the comparisons are horrible, but it's true. Compare the quantum mechanics, the relativity, all the particle physics, and biology is the same thing. But this is what I mean with this.
have more biology have recently also.
Biology has, yes, because was developed a little bit later, but even so, there are it's still different. The big science, I would say big science, really not big. Nowadays we call big science with everything which is associated with big amount of money, but I call big science something big in importance. No, the really important science, the fundamental concepts, particularly about biology. I think the evolution theory is the most fantastic, the most important achievement in the many centuries behind us. This is not comparable with small things that you discover a new protein or this, because these are things that they don't make any revolution in your concept. They can add some new information about, of course, the universe is infinite and you have many galaxies and many stars and many animals. You can add more data for your collections of data, but conceptually, you are not making a revolution in biology. You are not making new revolutions in physics. Possibly, I think, Alexander, maybe you have some complaint about that. People think that indeed we are doing some revolutions in physics, but we don't know about them. It's true, there are still some people that try to do something really important, but we have to wait the time just to evaluate whether these ideas are successful or not. And once we evaluate, once we say, not about our time, don't think about what we are doing now in 2024, but you can think about what was produced in 50 years ago in the 70s. Once we review the history of science and we say, okay, let's take 10 years, 20 years in the middle of, and what was the most important thing? Well, I think my impression is a subjective impression. I'm not talking from an absolute point of view. My impression is that the rhythm of very important science is being decreased. The rhythm of revolutions, the true revolutions, not minor things, but the true revolutions is being decreased. The amount of papers, the amount of science, the amount of money in science is increasing, but this has nothing to do. There is no correlation between
Inversely proportional to significance, presumably.
Yeah.
No, I'm in agreement here. Yeah. So, yeah. Well, I'm not. You say you would be too pessimistic with respect to new revolutions. You say the golden age is kind of over in physics, if not in science in general. So, I mean, yeah. But I would agree on that as a matter of fact. It's just that if you observe the structure of scientific of laws of nature, if you observe constants of nature, I would say that, well, there is something to be discovered yet. I mean, we still don't have the guy who explains the fine structure constant. He who calculated it in his computer, right? So it might be too difficult. Maybe it's really above the human mind. Maybe we need someday super intelligence to resolve that riddles, but the riddles exist. I mean, there are some give me a calculation of the mass ratio of the proton and the electron. It doesn't exist. or some very fundamental questions. So this is so. I mean, I would be pessimistic as you, as a matter of fact, as an observer of science. I see also the decline of real revolutions, but I would not exclude, as a matter of principle, that we can make also huge progress. Yeah.
I agree. I'm not a prophet. I cannot guess the future. Maybe in 10, 20 years, somebody discovers what you say, they can explain the fine structure constant in terms of something more fundamental physics, or can discover finally the particle for dark matter, and it's a big discovery. Well, it's possible. It's possible. We have to observe. I'm just observing the trend in the last years, in the last 50 years or so. If we continue with the same trends, I see that we are going down. This is the thing. It's not only about science, it's about culture in general.
Yes.
Except, well, if you talk about informatics, computers, we are better than ever, of course. So with technology, even medicine has all the things has to do with applied science are being quite successful, better than ever. But I talk about fundamental science, about knowledge, about our view of the universe in a philosophical way, our perspective. There were many revolutions in science. Of course, everybody has in mind the revolution of Copernicus, that we are not the center of the universe, or Darwin, or so, but there were many others. Possibly there is still place for something. I'm not saying that we have discovered absolutely everything, but I see more from many points of view, not only from the purely scientific point of view, but from a historical point of view. That I see that our society, at least the Western society, I don't know other countries.
You have been in China.
Well, I have been in China, but well, the China are doing also a science like in the Western, so it's the same thing. Our culture, our science, our art is a product of our way of being, our society. Our societies are some way exhausted in some way. So the societies are like human beings. They have a life. They are born. They grow up. They develop, and they are not forever. You cannot. There is not. We don't know any society that has been forever there. Any empire or forever. There is always some decadence, and this is due to that society becomes exhausted in some way. There are many mechanisms why this happens, and this is not anything new. For instance, just to mention one fantastic work, a German, the Oswald Spengler, The Decline of the West.
It came to my mind when you mentioned before. Yeah,
this is fantastic work.
Well, he's outdated clearly in a couple of ways, and also people have attacked him maybe for good reason. But I mean, it's definitely worth just to take a look on the.
No, but maybe the examples, of course, maybe he's wrong in many aspects, and particularly about science, it was not totally correct. But the general perspective that the societies are not forever, and there are periods in which you go up, you get the maximum what you can reach in your society, and after that you start to decline. Because this is like life. A person that is 90 years old cannot be so energetic as a person who is young. And we are very old. This is the thing, particularly Europe. Europe they call it the old continent, and it's really true. Our culture is really old. This does not mean that this is the end of the humanity. Possibly there will be new civilizations that will start to create culture in a different way, in a different sense. But this is just a different thing. Another aspect that I would like to remark is that we think that science is something common to all human beings. And we have to bear in mind that science is something proper of the Western civilization. Not all. Many civilizations have developed some kinds of philosophical ideas and other approaches to nature, other connections with nature. But this particular way in which we have developed they try to make understanding mathematically many concepts of nature. Well, this is a product of our society. And since societies will not last forever, possibly this way of doing science will not last forever. Possibly there will be new ways to approach to nature. We are now obsessed to making big catalogs of all the stars of the universe, all the animals, all the species. But this is our particular obsession as a civilization. Possibly other future civilizations will not have the same idea. They say, okay, let's go to do a bigger particle accelerator, an even larger space telescope. This is our particular way to approach to nature, but this is not something universal. Possibly the reality is universal. The universe is the same universe for all human beings, but the way we approach to nature, just trying to understand nature, this is something derived from the Western civilization, basically. Nowadays, China and other countries are doing the same game, but because they are influenced by our civilization.
Okay. No, I mean, I agree in many ways before, in particular where you highlighted the difference between applied science and technological developments, which are fantastic, and the very fundamentals of the laws of nature. And I also related that to a difference in culture, yeah, that we shifted from being interested in the very fundamental laws to developing fantastic stuff as computers and technology, and that's so far I agree. I also agree that we have a strong underestimated correlation between scientific predominance and also political military power, yeah, as we observed. And in that respect, Western culture dominates, even if I think it's a little bit a misnomer because it originated from Europe, and then now it has become something at least a little bit different in the American way after World War II. Applied science and less fundamental questions. So, and everything is called Western in this respect. I'm not sure I agree in the sense, and I would disagree probably also with Spengler here that I mean, you can call me a Westernist, but I think there is something new and exceptional in the scientific approach as such, because it's not just one of many cultures. It's that method of observing and trying to find mathematical laws of nature.
Absolutely.
That's really something new. That's something exceptional, and that's combined with other cultural developments. The Kant, think for yourself, the Enlightenment. Also, this is, I mean, that's a decisive step. That's more than just one of several civilizations. That it's very characteristic, I would say, of the human species here, at least. And I wouldn't sound too relativist here. On the contrary, I think it's something very fascinating in science that even if you imagine other civilizations living out there in the galaxy arms you're investigating, or in other galaxies, if there are intelligent species, they will also ponder on the fine structure constant. They will write it with a different number system, presumably, but the very fact that this is a riddle nature poses is the same thing, and that's incredibly fascinating. They will have a look at the same periodic table. So that's in a way a mentally unifying thought of science. I would dare to call universal in that respect. So it's not just some culture and some other guys in the universe doing something else, right?
Absolutely. I sign what you have said and the importance of science, and I am I'm a scientist, but I also admire scientists. I think it's something great we have created. It's not a minor product. What I mean is that well, it's fantastic. Like many other things, our culture has created many other things, the music or the paintings or whatever, and literature. There are many other manifestations of the culture, but we have to keep this in mind. Science is a manifestation of a culture, and not all the cultures have the same way to express the way of doing civilization. You mentioned China. China has some basic science, but has not become interested in science until now, until the 20th century. And it's a big civilization. You can examine that during 5 centuries, they have produced very important things. But however, they were not making calculations of the orbits like Kepler or this kind of mathematics, because it was not their interest in that time. Maybe they were producing poetry or other things which are also important. So
very interesting.
Summing up, I'm absolutely a defender of the scientific values, and we should be proud of what we have in the sciences. The science that has been produced in Europe in the last 4 centuries is fantastic. It's an intellectual achievement, much better than what can be produced in some small groups, human groups in Africa or in Brazil. I think there is something great in our science. Nonetheless, even if there are many truths in our science, we should not become dogmatic with the value of science. Science is not a religion. Science is not a value. Science is just something that we can enjoy for people who like mathematics like me or physics, but it's not a must for all the civilizations. There are people who say, well, I need science for making applications, yes, but this idea of understanding the universe maybe is not so important for everybody.
Yeah, I agree. I forgot to agree on the point before, because you were saying, yeah, being very related, we are also going down the same hill. Civilization as a whole, and also science has problems. So I come back to that point, you were addressing a specific, you called it a threat to science, to openness in science. You wrote even a book about, what's the title? Diversity, Inclusion, and Equity as a threat to
and the threat to academic freedom.
Ideology, unfortunately. So
I have not written the book. I was editor of this book. It was a collection of papers of many authors.
Even courageous.
26 different people. There are nowadays a lot of information in digital media and internet. So I thought it would be an idea just to collect many papers from many different countries, many different specialities, not only scientists, but also humanities or many other people working either in universities or in research centers. And they express in these papers some kinds of problems that they have to express their ideas, because they are in some cases not politically correct, particularly with this topic that you mentioned in the title of the book, the diversity, the inclusion, the equity, that people call it usually the woke ideology. Woke ideology nowadays is a new dogma that tries to remove all the critics around the world, and this is something against the principles of the Western civilization, at least in the last 2 centuries. I think freedom is as important as equity. I recognize that, of course, we have to fight for removing unfair situation, discrimination, in particularly and we should try to be better. But we cannot go to the opposite.
Quality of opportunity, I think, is the key, right? What we want.
Yes, but there are many ways to do that. You can defend your feminist ideas, or you can defend. But the thing is that in the moment in which you want to be to have the absolute value, and nobody can criticize you, this is what becomes problematic from an intellectual point of view. Maybe from a political point of view, maybe it's necessary sometimes just to forbid some things. But in an academy, it's not a good idea just to forbid discussing ideas. No. There are many examples, not only about the question of the gender, also about the race. But
yeah,
there are many examples, and they are very serious, especially in the Anglo-Saxon countries, which is curious, no? Because the Anglo-Saxon countries were some of the first nations to defend the democracy and the freedom, and now they are doing just the opposite. We are in the opposite direction, but it's not good for the academy. Even we are talking about some cases. For instance, now I remember the Watson, the famous Nobel Prize in medicine for the of Watson and Crick was rejected in some university because he said something about the question of the race and the equity.
People didn't like, yeah.
But he has not done anything wrong. Even he has not claimed that we should forbid black people to enter. No, it was nothing political, just expressing some ideas. And since these ideas were not sympathetic with the system, they rejected him. But like him, there are unfortunately tens or hundreds and hundreds of cases that are suffering this witch hunt. I will call it. Of course, they don't burn anybody, but they are ruining. They are wrecking the lives of many people professionally, at least. No, and it's very sad. It's very sad that we have be fighting so long time, at least since French Revolution, for these ideals, for freedom to express our ideas, freedom for the journalists, also freedom in academia to express your ideas. So long time fighting for that, and now in few decades, because this is something that is happening mostly in the last 20 years or so, we are going back very quickly, and the future can be even more pessimistic. So it's good from time to time.
Wasn't there a scientist having difficulties with, I mean, statistics about women publishing in science, and then I don't know, remember something very strange. He got fired because he said something which was wrong.
Yes, there are many cases. I have. If you want, have a look at this book, this collection of papers, and you will have a catalog.
I'm not afraid to put it in the link of this video. Yeah. I mean, that I see the danger that we are increasingly driven by ideology, that there are some questions you better don't touch, and this is harmful on the long run, because you need, I mean, the pursuit of truth. You cannot put some ideology, you cannot put taboos somewhere. You have to take the world as it is in all its sometimes brutal honesty. Yeah, even if you don't like it, there are some facts that we can't deny. Yeah,
absolutely, yes.
Yeah. That's a kind of an unfortunate development. Yeah, I'm grateful that you're one of the people speaking out. Aren't you a member of the International Astronomical Union, rightly in that division, or was that prompted you to do that collection in your book? Or
I'm a member of the IAU, but I do not join the meetings, or I do not participate in any division in general. I'm a simple member.
Okay. May I, yeah, before we finish, come to a couple of, again, scientific problems, or maybe, yeah, maybe things we might even disagree or something. People shouldn't think we are afraid of disagreement, because, I mean, we're two scientists, and we can say we're honestly struggling to become smarter. But yeah, sometimes you evaluate evidence in a different manner, and you have different ideas or a little bit of different background. You may maybe too optimistic for your taste something, but I said that, well, observing science as a whole, and well, focusing on revolutions. Yeah, my favorite example is that once you understood that the electric and the magnetic constants were related to the speed of light, that was the true unifying idea from optics to electromagnetism, and that's what brought civilization ahead. So, but technically, you're just reducing constants of nature. So, yeah, long story short, I'm very interested in the origin of constants of nature, and I really like the idea of something like the gravitational constant, big G, to be explained by the mass distribution in the universe, idea which was put forward by Dickey and by Sharma and goes back, of course, to Ernst Mach. But you're not enthusiastic of that or skeptical, or would you comment?
Well, no comment. Simply, if somebody can reach, as I say, to explain the fundamental constants of physics in terms of something even more fundamental, well, this will be something important for physics, but not necessarily will be like that. That we have some constant does not mean that there is something behind. Maybe it's just a parameter. We don't. I don't think that we should find explaining the speed of light, the charge of the electron, all the Planck constant. Maybe they are.
Sometimes it's not possible. Sometimes it's not possible. Sometimes it's not possible. But I mean, also with your philosophical background, I'm not sure how much you support the idea of simplicity in fundamental laws. But well, given that it's not a stupid idea to search for simplicity, I mean, wouldn't that be a big progress or desirable? Or on the other hand, aren't numbers like big G the gods of modernity and nobody questions it? Why it's 6.67 and not 5 point something else? I mean, it's not satisfactory, right? Or
I have no any opinion about that.
you don't.
In principle, for me, mathematics and the formula and the parameters which are in the formula are just simple ways to describe what is important, which is the observations. If we need to put G to 6.67, 10 to minus 11, in order to fit the motions of our planets, well, this is what we can get. If there is something behind or not, well, possibly yes, possibly not. I have no preference at all. This question of simplicity, everybody agrees that it's better a model with a lower amount of parameters. Of course, the heliocentric model is better than the geocentric, and instead of putting a lot of epicycles and all that, it's true. But sometimes nature is complex. Sometimes we cannot reduce everything to fundamental ideas. This is, of course, this has been the dream of many physicists in the last century. This kind of unification. No? Why we should have the relativity and quantum mechanics separate realities? There should be a unification of everything. Possibly, and sometimes these kinds of approaches are successful. The electromagnetism was the Maxwell was a fantastic advancement in physics. We could understand the nature of light combining with our ideas in electricity and magnetism. It was a big advance. But sometimes things are separated because are separated. No. Simply, there are different ways to see the nature, and if you concentrate to a small scale, the microscope scales and the big universe, they have possibly the same laws, but in one hand, in one aspect, in one scenario, you have to apply some laws and rules, and in other scenario, other different rules. I'm not surprised. This is a philosophical question, I would say, Alexander.
No, I agree that it boils.
This is why how I understand. Some people understand that mathematics is the last reality of the universe. So the objects that we observe are just appearance. They are just. We could close the eyes and see the universe without making any observation, because everything is a question of mathematics and intelligence. This is a Pythagorean approach, I would say. No? And then there is another perspective, which is more empirical. We say we don't know anything. Even I don't know whether mathematics can describe everything, but it works. Since it works, I apply it, and it's a useful tool. But mathematics is not my God. And the last reality is not understanding the mathematics which is behind the constant of the physics. My goal is just trying to describe everything what I observe. And if I need to introduce 20 new parameters, maybe I have to introduce 20 new parameters. Better to introduce only one, and with only one parameter explaining everything, of course. But if we cannot, this is what we have.
Yeah. Well, I agree and disagree. I agree in the respect that not necessarily math is fine and something very good. I mean, you know, I'm a fierce critic of string theory, mathematics without touch to reality. That's nonsense. But on the other hand, it's not only a philosophical fancy, I guess, but I think there is some historical evidence that this explaining of constants of nature, which, I mean, Hertz's discovery of electromagnetic waves was, if you want, a explanation of one constants of nature. Bohr's atomic model was another one. So I think this getting rid of constants is, yeah, some historical evidence that this is the way progress is done. And well, I'm a little bit more optimistic in that respect, but if you don't agree, that's
No,
fine. You're more
no,
skeptic and say, come
as I
along with
say,
the theory. I'm waiting as an observer.
I do not reject this idea. I think it's fantastic, but I have not any particular point of view.
Mhm.
Uh,
It's fine. It's okay. Yeah. Yeah. Another thing I want to address, and maybe we also disagree a little bit here. Yeah, you have a lot of observations. You have a lot of models which digest these observations. You mentioned the standard model of cosmology. You're expert in, or expert in testing that. But that means you have certain doubts, let's say, if dark matter exists at all, or if dark energy exists at all. So where to draw the line between undeniable evidence? You mentioned the craters on Moon. Nobody, no sane person would deny their existence. And the other guy who is convinced of dark energy and forget about anything else, but we know it's established and yeah, let's go beyond and build other models on top of that. So it's my point is it's difficult sometimes to draw the line. You're a skeptic of dark energy. You're convinced of craters on the moon, but there is something in between. Different thinking people can have different opinions, right?
Yes, of course.
Yeah.
The world is not neither black nor white. There are a
Yeah.
lot of
And
grays in
sometimes
between.
just
And many topics are discussable. Maybe we don't agree. Maybe in some topics, some people think, no, this is absolutely true. Other people think that is something discussable. Yes.
This being the introduction, I mean, you know, in my first book, in my first chapter, I praised the discovery of the cosmic microwave background inside it. It was so beautiful, and future civilizations might nod their heads in agreement and in appreciation for humankind for having discovered that. But honestly, in the meantime, I'm kind of undecided because I see this as a big science project, like accelerators, like gravitational waves, with a strong desire to see something, with a yeah, with a strong pressure to fit the data into the model. You're saying that would be independent evidence for the dark energy or dark matter, even the cosmic microwave background. I see a lot of, I mean, technicalities, the dirt in the science to be a little bit swept under the rug. I mean, it's kind of ambitious to remove all the galactic foreground. Isn't that ambitious? If you look at these wavelength in microwaves, I mean, how much contamination before we have. Do you think that can be done in a reliable manner, or have you, well, slight saying, oh, well, the technical specialists have all this done, it's fine. I believe that map, or do you have some slight remaining doubts?
I have doubts. I have been working in this field also in the foreground contamination of our galaxy to the CMB. I did it a long time ago, maybe 20 years ago, with the first data of the COBE and W map. And things have progressed. Now the groups have better techniques, and they can clean better the maps because they have more complex models. But even so, from time to time, I read in the literature from other papers that still in these clean maps that should be clean of foregrounds, you make the correlation and still you find some correlation with the galaxy. So this means that there are some residuals. And this is because, of course, we are making many extrapolations. Even if your model is very good, it's very complex, the galaxy. You have to observe the galaxy in far infrared, assuming that they have the same power spectrum and extrapolate it to the millimetric. You have and this depends on also in the region, because it's not the sky is not homogeneous. Maybe in some region of the sky has some spectral index. You go to another region, changes the spectral index again. So there are it's crazy. So you cannot do 100% clean. You cannot never do it. There will be always some residuals. Whether these residuals are negligible or not, well, this is something to discuss. My impression, and now, as I said, I have been working in this long time ago, but I have lost the connection in the last year. I have not touched the data in the last years. But my impression that it still is that the people is making the same errors. Even if they are doing better, they are the same errors than before. They are too optimistic. They think they can remove totally the foregrounds and with very high confidence. And this is perhaps not totally correct. Not only the foreground of the Milky Way, but also the residuals produced by other galaxies. Other galaxies also.
Yeah. I mean, there are low surface brightness galaxies of which we don't even know how many surface brightness galaxies are out there, and they would be hugely dominate the respective condition in that field.
And as I say, as a matter of fact, from time to time I see new papers claiming, look, this map should be only cosmological CMB, and I make the correlation with this and that, and I find correlations. How is it possible? And the correlation at several sigma. I mean, it's not by chance. It's not a pure fluctuation. So there is something there, possibly. And for sure, this affects our measurements of the cosmological parameters. This obsession of nowadays of the cosmologists just to measure this high precision cosmology. We want to measure with 1% precision the Hubble constant, the omega m, omega lambda. This is if you take into account all the systematic effects that are there, it's not 1%, it's more.
If you want the philosopher you should surely appreciate, Ludwig Wittgenstein said, "Ambition is the death of science."
I like this. I read Wittgenstein years ago, and I think has very interesting things to say. Yes.
Yeah. Maybe one really last topic. I'm not afraid, but one we probably have the severest disagreement. But I'm not afraid. Why shouldn't we? You said that one said that it's about heterodox scientists and outsiders trying to revolutionize the field. Maybe you're already guessing what I'm talking about. And you said these people are sometimes just too lazy to do the serious work to publish here and there. And for that reason, justifiably, they're not recognized. Now, I'm talking about the son and my friend, I have known him, Robbie Tai, who, came up with a totally, you may say, crazy idea about the sun, and he's questioning if it's really a gaseous model. And well, without now going into the factual controversy, I mean, what I can say, he's definitely not lazy, or he's at least a serious scientist. I mean, you could hand out him a Nobel Prize for ultra-high field nuclear magnetic resonance. It's so this is certainly not the case, but you're very if I remember, you're very reluctant to challenge.
No, I don't think these people. It's the opposite. These people work very hard and they are very enthusiastic about science. It would be much better for professional scientists to be as enthusiastic and as hardworking as many of these people, and even without receiving any salary for doing that. So I admire many of these things. But the question is that science nowadays, not 2 centuries ago, it's a slow process, and you have to follow some stages. You cannot go the first day you go to a faculty of physics in the university or a research institute. You cannot say, hey, look here, I have here my revolution in science. No. If you want to participate doing science, the normal process is, okay, you come here, you do your PhD. After your PhD, you want to be a specialist in the sun. Of course, dedicated some years to study the sun, publish some papers of normal science, maybe 5 or 10 papers of normal science. And after that, once you are some specialist in some sense, you can say, okay, I already know many things about the field. It's the time to produce a revolution. But normally, many heterodox outsiders that are not professional scientists, they work in a different way. They have no patience. They say, okay, I'm very old because now I am retired and I have no time just to start a new career in science, and I have no interest because I have my own job. The only thing that I want is just to produce a revolution in science. Maybe it may happen. I don't say no. Maybe one in 1 million by chance may happen that there is really a revolutionary idea. But my experience with many heterodox cosmologists and amateurs and these things that I receive many contacts regularly. My experience is that
that's out of question. Yeah, of course. Yeah,
is that usually they need. Maybe the ideas are brilliant, I admit, and they are good ideas, but they need to dedicate more time. It's not that they are not lazy, simply is that they have not resources. One person alone, isolated, without experience in the field, and a newcomer is very, I would say, almost impossible that produce a big change in our ideas in this particular field. You need to dedicate a long time. And this means starting when you are young. This is the same like any other profession. For instance, I'm very fond of classical music, but unfortunately, I'm a terrible pianist. I'm very bad.
So I am.
And I say, oh,
should play together.
I should have started when I was 5 years old, and just and giving my first concert when I was 15, and this is the way to do a pianist. But if I try to start my career as a musician at my age, possibly I have zero possibilities. No, science is not so extreme, but it's just an example. No, but science is a profession, so we should not underestimate the people who are professional scientists and they are specialists. Possibly they are very conformist and they don't want any revolution. It's true, but they have a great knowledge in their fields, and it's not that they are ignorant and they are waiting for some genius to discover something new. No, if something was not discovered in a particular field when there are hundreds and hundreds of people that have dedicated many tens of their years, we have to think that possibly this is not the way, or if it is the way, it will take a long time. So I don't believe in this spontaneous idea that nobody realizes among thousands and thousands of people, and only one person in the planet realizes of this idea because he's a genius. This is very romantic idea of the science, but it's not how it works.
Very rare, very rare. Yeah, Alfred Wegener was one of them. But I mean, as a matter of fact, we have these.
Wegener was a professional scientist in any case.
Yeah, but he was a meteorologist. He was not a geologist. That's an important. A geologist ridiculed him, and he said, "Oh, he's a meteorologist. He doesn't understand geology." So anyway, as a matter of fact, we have in science we have these dead ends of any length. We have 5 years into until Hahn realized that he has split the atom. It was very short. You had, I don't know, phlogiston, I don't know, for 80 years. We may have dark matter, we don't know. And we had medieval astronomy for, I mean, the wrong concept for something like 2000 years, order of magnitude. So it's kind of, I mean, it could happen that we have these dead ends, these wrong paths for a long time. And yeah, regarding publishing, doing normal work, as a matter of principle, I would agree. But you called me before a more expert in particle physics. I'm not an expert in this respect. And frankly, I hadn't a chance even to publish there because it was, very, very complicated to enter the institutions, to enter the data, and so on and so forth. And so, but it's not that I'm lazy or I'm not willing to. I would be thrilled to analyze, say, raw data of Hofstadter's scattering experiment in 1962 or something. but the point is here, you're effectively, you cannot start wherever you want. You have to be a member of the community in certain fields. So it's kind of hard to do that normal science work you mentioned before, and sometimes it's might be also impossible. So what I'm trying to say, I mean, even if you not enter the field of particle physics, I think that I have legitimate concerns from my study of the field that certain problems are not addressed. Certain things are swept under the rug. Certain methodologies are not scientific in a strict sense. So from the outside, even if I don't go into details, I have a legitimate skepticism towards certain things. Yeah. So yeah, as I said, while as a matter of principle, I agree, but that's not possible in all cases. And yeah, if you have a very long story, even an accepted model of stars that are gaseous, as the gaseous model was established some, well, order of magnitude 100 years ago. And now you say, oh, it might be liquid metallic hydrogen. Why not? As a matter of principle, I mean, I see the possibility. It's very, very, I mean, if you say it's very unlikely from your perspective, okay, that's fine. But yeah,
I'm not a specialist in the sun or stellar physics, but for me, it sounds very strange that no specialist in the sun accept this view, and only few outsiders see the reality. It looks suspicious, at least I would say. I cannot enter in detail because I don't know the details. No?
Mm-hmm.
But of course,
yeah, what we can do is I like at this point I always like to go to history, and I find very few particle physicists agreeing with my views, but I would say I'm able to demonstrate that if you open biography of Dirac or Heisenberg, and then you're finding something which speaks in favor of what you think about certain things. So this is also the one we should include, and I guess at least from a general perspective, we are on the same boat here because you are also in history and you're also in philosophy, and that's yeah, an integral part of the scientific enterprise.
I understand you perfectly, and I am with this spirit. I think science should be done with free thinkers, not in big organizations. It should be something more anarchical, I would say. No, this will be this will be a good direction for science. I hope this for the future, but at present it's not like this. And even we cannot compare with the times of the beginning of 20th century. It's totally different. Einstein was working in a patent office and at the same time was producing the three papers, the fantastic paper in the 1905. Nowadays, I think it's almost impossible that a person who is a totally outsider just starts to write a paper and makes a revolution. Maybe or the probability is so low that it's almost once every 200 years it may happen. But
yeah. For I think regarding the fundamentals of space-time, what I believe are the unsolved riddles, I also guess this is very unlikely. And yeah, recently I have a little bit of hope that we will develop some intelligent machines, but that's maybe a personal optimism. But yeah, definitely, as a revolution in science will be accompanied by also other revolutions in society. Yeah,
I think so. I think so.
Yeah. Okay. Anything else you want to mention? You want to, a message you have to young researchers, to students, to people out there interested in physics?
I may summarize in 2 or 3 points. One, that science is a wonderful career, a wonderful work, and I hope people keep the enthusiasm. The important thing of doing science is being enthusiastic, not don't being attracted, just getting stability, the position. I have to buy a house. No, forget about that. If you think have this mentality, better work in a bank or in a company, not in science. But science is something really very important and very nice to do. Other thing is, well, I have to prevent, especially young people, how the system works. It is like this. It's the human reality. We should we have our ideas. All of us thought when we were young, when we were 20 or 25 years old, that science was more a pure system in which the good ideas get successful and the bad ideas are rejected.
Church, yeah.
And the people who are, we were rewarding the intelligent people. No, I have to say that nowadays in science, the most appreciated scientists are not the most intelligent ones, are not the people who dedicate most time to science, but are the people who dedicate more time to administration of science, to make phone calls to important people to get some money. These are the people who get success in science. It's sad, but it's better to do that. Anyway, even so, even in this pessimistic scenario, it's better to live in the shadow, just making our small science and enjoying to do this science, rather than being embedded in a lot of meetings and video conference and a lot of tasks that has nothing to do with science. So I encourage people just to think about the real science, but better, of course, in a professional way, because there are many more chances.
Yeah, I think that's a very good two-folded statement. Issue a warning also to young people that it's a harsh reality of business and career and ambition and things you don't want, bureaucracy and stuff like that. But at the heart, there is still let's say a nucleus of sane science, which is a fantastic human activity. And
I agree.
Leads us to the basic questions of our existence and the law of natures, and that's something very, very attractive. And I'm glad that I met you, this representative, and to everyone else out there, I can only recommend your work. You find it in the description. Martín López Corredoira has very broad interests and interesting research. Thank you very much, Martin, for the conversation.
Thank you very much, Alexander, and to all of you. Bye.